In this video, we're going to introduce exponential functions and their graphs. So we've dealt with functions where we've had a variable in the base and a constant in the exponent. An exponential function flips around those roles. So an exponential function is a function of the form a to the x, where a is a number, x is the variable. Now we do put some restrictions on a. We want a to be a positive real number, and we do not want a to equal 1. Of course, the reason why we want a to be positive is because we don't want to have a negative in a base, because that causes all sorts of domain issues. If we use negative 1 to the x, then we wouldn't be able to put 1/2 in for x, because you would get square root of negative 1. That's equal to I. We're dealing with real valued functions here, numbers that come out and be real, that come out as real numbers. So we don't want complex numbers to come out. So 1/2 causes an issue, 1/4 causes an issue, and so on down the line. Also, we don't want a to equal 1, because if a is equal to 1, then we just get f of x is equal to 1 all the time, and it's a constant function, and we want all exponential functions to have certain properties, and the constant function won't have these properties that we want. Using this definition, making sure that we don't put in negatives allows the domain of any exponential function to be negative infinity to infinity, because we can take any positive real number to any power we want. We also notice that when we put 0 in for x, we get 1 out, no matter what happens for a. So the y-intercept of the graph for any exponential function will be the point 0, 1. Let's look at a couple specific exponential functions and see what their graph looks like. Since this is our first exposure to exponential functions, our only real recourse for figuring out a graph is to pick some values for x, get some values out for f of x, and play connect the dots. So let's do that for both of these functions at the same time. Let's just choose x equal to -2, -1, 0, 1, and 2. Putting those values in for 3 to the x, well, 3 to the -2, the negative tells us to flip it upside down, the 2 tells us to square it, so we get 1/9. When we put in -1, we get 1/3. When we put in 0, we mentioned a bit ago, we get 1. When we put in 1, we get 3 to the first, which is 3. And when we put in 2, we get 3 squared, which is 9. So those would be the points that we would be looking to plot for the f of x equals 3 to the x. Do the same thing for 1/2 to the x. Notice in this case, the numbers are going down. We start at 4 when we put in -2. Think about why that's true. We get 2 when we put in -1. We get 1 when we put in 0. 1/2 when we put in 1. 1/4 when we put in 2. So notice that as x gets bigger, f of x gets bigger, but g of x gets smaller. And here is a rough graph of each of those functions. Here's your f of x equals 3 to the x. We're getting bigger in this case. Here's your g of x equals 1/2 to the x. Your graph, your y values get smaller. In this case, it goes down. So let's make some observations about these graphs. Both of the graphs are above the x-axis all the time. The range is 0 to infinity for both graphs. Notice that both pass the horizontal line test. So that means that both of them have inverse functions. And we're going to talk about the inverse of exponential functions in a later video. Both get closer and closer to the x-axis. They both have a horizontal asymptote of y equal to 0. The first one was increasing, and the second one was decreasing. So let's summarize what we've seen so far. So here's properties of the function f of x equals a to the x. The domain is all real numbers. The range is all positive real numbers. Y-intercept is 0, 1. Horizontal asymptote of y equal to 0. It's increasing if a is greater than 1, and it's decreasing if a is between 0 and 1. Like I mentioned before, exponential functions are 1-to-1. So we're going to use this fact to help us solve exponential equations in this section. So let's say we were given the exponential equation 7 to the x equals 1/49. Our basic technique here is going to be to write both sides using the same base. So there's not a lot I can do with the 7, but the 1/49th, I notice that I can write this 49 as 7 squared, have the same base. I'm not quite there at this point because I got the 7 to the x is on top, if you will, on the left-hand side, whereas the 7 squared is on bottom. But we can rewrite that right-hand side using a negative exponent. So we get 7 to the x equals 7 to the negative 2, and now I have two outputs of an exponential function that are equal to each other. I have 7 to the x equals 7 to the negative 2. Since the outputs are equal to each other and the functions are 1 to 1, that tells us the inputs are equal to each other, and we get the solution of x equals negative 2. Let's look at another example. We have 8 to the 3 minus x equals 1/16 to the 2 minus 3x. Again, our big goal here is to try to write each side in terms of the same base. Well, in this case, we notice that both of them are easily rewritable as 2 to a power. 8 is 2 cubed, 16 is 2 to the 4th. On the left-hand side here, we notice we have 2 cubed, and then that whole thing is raised to the 3 minus x. In this scenario, we can multiply exponents. On the right-hand side, much like what we did in the previous example, the 2 to the 4th is in the denominator. We can move it up to the numerator by making a negative exponent and writing it as 2 to the negative 4. Now this right-hand side looks like the left-hand side in the previous step. We can multiply our exponents. And now we have the equation 2 to the 9 minus 3x equals 2 to the negative 8 plus 12x. Again, now we have two outputs of an exponential function. Since the outputs are the same in this case, the inputs must be the same. So we can equate exponents and write it as 9 minus 3x equals negative 8 plus 12x. Now we just need to solve for x and get x is equal to 17 over 15.